Hello friends, I am going to discuss digital circuits. Particularly in this subject, I will be discussing sequential circuit. I am Dr. Parimal Shah, Assistant Professor from the Department of Electronics and Communication Engineering, Bhagalpur College of Engineering, Bhagalpur. So let me discuss the outline of this video lecture. So I will be introducing the subject first, then I'll follow the NOR gate and its properties. Then I will discuss the basic flip-flop with NOR gate. And then I'll discuss how this NOR gate is converted into the equivalent NAND gate. Again, how clock is added to the SR flip-flop. And then I will discuss the compact characteristic table of SR flip-flop. And finally, I'll discuss the excitation table of SR flip-flop. So coming to the introduction part. In digital circuit theory, sequential logic is a type of logic circuit whose output depends not only on the present value of its input signals, but on the sequence of past inputs, the input history as well. This is in contrast to combinational logic, whose output is a function of only the present input. So let me discuss the NOR gate before going to the SR flip-flop. What is NOR gate? It is a gate with two input and one output, and it is equivalent to the OR gate connected with the NOT gate. So its truth table is very obvious. So AV is the input, Q is the output. When you apply both the input 0, output becomes 1, and remaining all the three cases, output becomes 0. So based on this truth table, we can find its properties. We can define its properties. Like first property is output of this gate is 0 whenever at least one input is 1. So this can be shown in this symbol. Whenever one input is 1 of this OR gate, output becomes 0. What about the another input? It can be 0 or 1. Similarly, the another property is output of this gate is 1, as you can see here, if both the inputs are 0. And same can be shown here, both the inputs are 0 of this NOR gate, then its output becomes 1. So these two properties are very basic properties of NOR gate. You can see here that whenever at least one input of the NOR gate is 1, output becomes 0, irrespective of the another input, whether it be 0 or 1. And when both the inputs of the NOR gate is 0, its output becomes 1. So we can see, based on this property of NOR gate, we can discuss the basic flip-flop with NOR gate. So here is the NOR gate, and suppose we have applied 1 to the what is now SR flip-flop or SR latch first. This is the SR latch. Here two NOR gates are connected back to back. So this output is connected to input of this, and its output is connected to this, and this is the R reset input, and this is the S set input. Suppose 1 is applied to the S, then output of the NOR gate 2 becomes 0 because of this property. And since suppose another input R is 0, and since this output has become 0, this will go to the input of the first NOR gate, and because of this 0, this output will become 1. So whenever there is input set or reset 1 0, output Q and Q dash will become 1 and 0. So this can be represented on the table SR Q dash. So SR is 1 0, then output Q and Q dash will be 1 and 0. Similarly, suppose now we are applying another input. So suppose this 0 remains 0 and this input 1 changes to 0. So both the set and reset input become 0. Now what will happen, since this 1 comes here, because this 1 is the previous output at the Q, and because of this 1 and this 0 input, this output 2 will turn into 0. Why it is happening? Because at least one input should be 1 to become the output 0. Now this 0 becomes the input of this gate 1, and since this both input are 0, output will become 1. So here we are seeing there is no change in the output. It 1 0 becomes 1 0. So we can take this 0 0 set reset and output 1 0 in this table. Now we will take the another set of input. Suppose this 0 remains 0 and this input R becomes 1. Now what will happen, since this is 1, the output will become 0 because of this property. Now since this 0 will reach here and this both 0 input goes to 1 NOR gate 2, the output will become obviously 1. Now again we can fill up this table 0 1 0 1, so 0 1 0 1. Again we can discuss the next input. Suppose this input remains the same 0 and this input becomes 0 again. So what will happen, we will pick up this 1. This 1 goes to here because this is the previous output, and because of this 1 and 0, this will become 0 because of again the same property. Now this 0 will reach here and both the inputs are 0, so this will become 1, and we can fill up here. Again there is no change. When both the inputs becomes 0 0, there is no change, the state is not going to be changed. Now input are 0 0 and output is 0 1, so we can fill up this table 0 0 0 1. And now we'll discuss the final input sequence. Suppose both 0 now changes to 1 simultaneously. What will happen? Both the output will become 0 simultaneously, and the table will be filled like this. Is the invalid case because a sequential circuit cannot have both the outputs same. Either one will be 1, another 0, or first one 0, another is 1. So both the 0 is invalid case, so we cannot apply both input 1 to the RS latch. So we can fill up this table 1 1 0 0. Now this basic funda is applied to the let me discuss now to basic flip flop with NOR gate and how it is being converted to the NAND gate. So same fundamental we will use to discuss the latch with NAND gate. So here we can see this is the NOR gate. AB is the input and output will be A plus B whole bar, which is equal to, using De Morgan's theorem, A bar into B bar. So this is equivalent to the inverted AND gate. So in this NOR latch we can transfer these two NOR gates into equivalent NAND gates. Here you can see this NOR gate is converted to this NAND gate and this NOR gate is converted to this NAND gate. So here we are saying this is the output Q, this is also Q, this is Q dash, and this also is Q dash. Now what can we do? We can transfer this NOT gate to here, and this NOT gate to here, so which is shown in this picture. And this NOT gate is moved back, this NOT gate is also moved back. Since this is Q and the output we are taking here, so this will become Q dash, because NOT gate is there in between. Again, since this was Q dash and another was Q, so this will become Q, this output will become Q. So we can transfer this circuit to equivalent this, because this two NOT gate can be represented by NAND gate like this. So these two circuits are similar. This is the SR latch with NOR gate, and this is the SR latch with NAND gate. So what will be the truth table for these two? For this characteristic table, which is called characteristic table also. So these are the all set. We know this is the truth table, as we have already discussed. Just I am repeating. So whenever there was SR 10, output was Q was 1, so which is called set condition. When both are 0, there is no change, 1 0, so this is called no change condition. Whenever R becomes 1, S remains 0, it turns output to 0, which is called reset condition. And when again both are inputs are SR 0, there is no change in the output, Q dash remains same. And when both the input SR becomes 1, output both becomes 0, which is invalid case, because in a sequential circuit both the outputs cannot be the same. So this is the very important truth table to discuss the SR latch. Again I will discuss, whenever S is 1, it is set condition, it will turn the Q 1. Whenever R is 1, it will reset the Q, means Q will become 0. And when both are 0 0, there will be no change in the state. And when both are 1, it is invalid case. Now let me discuss the flip flop, SR flip flop, and its equivalent. When we'll remove these two, then in NAND gate equivalent SR latch, if we'll remove these two NOT gate, it becomes like this. So what will be its truth table? So we know the truth table for this is this one, and what will be the truth table for this? It will be nothing but just opposite of this. So these two input must be converted, complemented. So here we are showing the truth table for this. So SRQQ dash is for this circuit. Here I'm inverting these two value 1 0, here I'm putting 0 1, and output remains same 1 0. Similarly for the another, these two are 0 0, here I'm putting 1 1. Here this is 0 1, here I'm putting 1 0. These two are 0 0, 1 1, here both are 1 1, here both are 0 0. So for this type of SR latch with NAND gate, 0 0 condition is the invalid, and what is happening when S is 0, it is set, and when R is 0, it is reset. So this is also called S bar R bar latch. Now we'll move to the clocked SR flip flop. So how to discuss clock? Suppose one clock pulse is connected to two AND gates, and one input is R and the input is S. Whenever clock is 0, both the AND gate will have the output 0. Whenever the clock pulse is 1, here both the output will become R and S. So this R will transfer here because this is 1, and this S will transfer here. So clock pulse is like a enable circuit. When it is 0, output remains 0. When it is 1, it enables both the AND gate, and these values are being transferred to here. Now we connect this NOR latch to the output of this circuit. So here again, when clock pulse will be 1, this RS will be transferred here, and the whole circuit will behave as a SR latch, but with a clock pulse. So whenever we will give clock pulse high, it will react as a SR latch. So this is the equivalent NAND gate of the SR latch with clock input. So characteristic table we can discuss once again. So same thing, Q, S, R. Now what is happening here? We are taking the input Q, S and R, and output is Q. This is called characteristic table. So whenever SR is 0, 0, there is no change, so output remains same, 0. Again, when SR becomes 0, 1, so this is R is 1, so output will become 0. Whenever S1, output will turn to 1 irrespective of the Q. Again, when both are 1, 1, so it is indeterminate case. It can be either 0 or 1. Again, here X I am showing the don't care also. Again, when both the inputs are 0, so it's no change, so 1 remains 1. When R is 0, R is 1, so it is reset case, so Q becomes 0. And when S is 1, it is set case, so this becomes 1. And when both are 1, 1, this is again invalid case, which is the don't care condition. So now we will discuss the compact characteristic of SR flip flop. So we are seeing here both the inputs are, for SR flip flop, both inputs are 0. And Q remains 0 to 0. Another SR input, here both SR inputs are 0, and Q becomes 1 to 1. So there is no change. So this will be shown in the characteristic table here. So when both the inputs of SR is 0, there is no change. So QT plus 1 becomes QT. So I am transferring this characteristic table to the compact characteristic table in this one. Now next input we can see, if both S and R becomes 0, 1. So here present state of Q 0 becomes 0, so remains 0. Again, here is the both inputs 0, 1. Both the SR is 0, 1, and in this case also 0, 1. What happens here? Present state changed from 1 to 0. So this can be shown here. When both the inputs are SR are 0 and 1, what happens? Output remains 0. Next case, when SR becomes 1, 0, output becomes 1. Again 1, 0, next state becomes 1. So this can be shown in the compact characteristic. Whenever SR is 1, 0, output becomes 1. This is the set case. And what happens when both the SR are 1, 1? This is don't care condition, and both the SR 1, 1. This again changes to don't care condition. So in the compact, we can show when both SR are 1, 1, it's an invalid case. undefined case, or we can say it's a don't care condition. So finally, we can discuss the excitation table. What is excitation table? Here we take the input qt and qt plus 1. This is present state, this is the next state. So there are 4 conditions. Based on that, what will be the input excitation? This is called the excitation table. So to discuss excitation table, we check this qt and qt plus 1. Here it is 0 to 0, and in this case also it remains 0. What about the input? So for these two cases, s remains always 0 and r becoming 0 and 1 in this case. So these two conditions can be entered into one condition. So present to next state remains 0 0, and s remains always 0 and r becomes 0 or 1. So don't care condition. Again we can discuss next case when present state is 0 and next state becomes 1. And the same thing you can see when it happens when s is 1 and r is 0, and it can be entered into excitation table. This present state is 0, next is 1. It happens when SR is 1 0. This is called set condition. So third case we can discuss when present state 1 changes to next state 0. It happens when SR input are 0 1, and this can be shown here 1 to 0, and here SR is 0 1. This is called the set case. And finally we can discuss when it remains present state 1 changes to next state 1 itself, and this is the here again another case. So what happens to SR? You can see R value remains 0 and S value becomes 0 and 1. So this is don't care and this is 0. So this can be shown in the excitation table when present state is 1 and next state is also 1. This happens only when R is 0 and S is 0 or 1, which can be shown from here. So this excitation table is very much important whenever we want to convert SR flip flop into another flip flop like D flip flop, T flip flop, JK flip flop. This excitation table works there. So now based on this characteristic table, we can discuss the Kmap. What is Kmap? When we enter QSR as the input and QT plus 1 as the output. So here the output is QT plus 1 and input is Qn is nothing but QT and SR. So there are the 8 possible input minterms which are entered in this Kmap, and when we minimize this 2 don't care comes here, and this is one quad and this is one duet. So its minimization is called the characteristic equation. So Q2 plus 1 is nothing but S plus R dash Q, and the condition is SR must be equal to 0, means both input cannot be simultaneously 1. So its symbol is nothing but here. So we have discussed the SR flip flop characteristic table, compact characteristic table, how NOR gate is converted into NAND gate, and finally the excitation table, and this is the final symbol. Thank you. Thanks all. I hope you will enjoy. This is my first video lecture using the PPT. Thanks.